So I will not apologize that there is too little birational geometry in my lecture, because actually I was originally invited for the other workshop. So actually I had a totally different crowd of people, but they were kind enough to put it here. Right, the other workshop was derived and would have been not derived either. So I will talk about a set of ideas that appeared in the boundary of topology and algebraic geometry. And I will recall the algebraic definition, or present the algebraic definition of a Koszul module. And here this is, right, so it appears in various works that I did with Mariana Aprodu, Raicu, Stefan Papadima, Alexandru Suciu, and so on. So let me just begin with an algebraic definition. So you start with V K vector space, and you form the symmetric algebra. And you fix once and for all K, a linear subspace in wedge 2 of V, and construction is subject to this choice. Then, right, so what is this? I will give a lot of examples, but let's just present the definition now. What is the Koszul module of this pair? So the Koszul module of this pair, the Koszul module of the pair V and K, which I will, so the Koszul module is unfortunately noted by W, because Koszul cohomology stands for something else. So is the cohomology of the following complex. So I look at K tensor S, so S is the symmetric algebra, has a grading, then goes into V, tensor S shifted by 1, and goes into S shifted by 2. Okay, and here this is the multiplication, delta 1, and this is delta 2, is the restriction of the Koszul differential. Right. So, so these are complexes of S modules. If there is a grading, as indicated here, and you take the cohomology of this. So maybe let me spell it out. So in degree K, in degree Q rather, so in degree Q, you have WQ of dk is the cohomology of K tensor SQV goes into V tensor SQ plus 1V and SQ plus 2V. Yeah? And so here the Koszul differential delta 2 sends something like U wedge V tensor F to U tensor VF minus V tensor UF, something like this. And delta 1 is just the multiplication. Yeah? Okay. So, and you treat this variationally. So the point is that you are going to treat this, you are going to vary K here, right? So this is part of the general philosophy here. Maybe I give an example here, K equals 0. Yeah. So you can do this for any subspace in wedge to V. In particular, you can do it for K equals 0. So then there is nothing here. So you just look at the kernel of this map. And I would like to record what you get. So in this case, you get simply the kernel of V tensor SQ plus 1V into SQ plus 2V. And, well, by the Euler sequence, this is canonically isomorphic to A0 on omega of the projective space, twisted by Q plus 2. Right? So, in particular, the dimension of this is unknown. You can compute it, but I would like to record it. Maybe I write it here. Is what is it? This is Q plus 1 times n plus Q, choose Q plus 2. N is the dimension of V. n is the dimension of V, so yeah. Okay. So, right, so of course if I had here wedge 2 of V, then this would be 0, right? That is the part of the exactness of the Koszul complex, and you take a subspace and you measure the deviation from the Koszul complex. That's the idea. Any questions on this definition? It's a simple definition. So the question is what's good for. So let me just describe. Yeah, so let me proceed with this algebraic theory for a while. So I have this this Koszul module. It's a module of the symmetric algebra. So then you have the support of this, Koszul module. So this is going to be some subspace in V dual, and it turns out that the support of this is actually the resonance variety. So it's what's called the resonance variety, and it's by definition the set of those V in a dual with the property that there exists a B in V dual such that A and B are not proportional, but when you view this as a functional, so A wedge B is a functional wedge 2B, you evaluate it to K, you get 0, or it lies in K per, and this is called the resonance variety. Of the ARBK. So the resonance is associated to the Koszul module.
Is there any good reason to call it the resonance?
There is very good reason. I will explain. Yes, so I think I'll give examples. Right? They come from topology, and then you will see. So essentially, resonance is a they are cohomology jump loci. I will get to this in a second. Okay, so this is something. That was maybe perhaps more algebraic. This is something very, very, very straightforward, right? In the sense that you see when is the resonance actually 0. And I add to it 0 here because you want to have it as a cone. The resonance is 0. Well, yeah.
So, sup is for support.
Yes.
Is it support inside the Grassmannian or support in which sense?
Support as a module. As a module, is a module over S. Yeah, I mean.
It's okay. It's inside the P of the.
That's right. Inside the projectivization of V. Yeah, that's right.
But you could as well consider something in the Grassmannian. I mean the set of decomposable vectors which are in the.
Not only I could, I will in a second. Yeah, right. Exactly. So okay. So let me just. Let me just write this down, and I'll come exactly to what Claire is alluding to. So this is 0. When is this 0? Well, actually, I'm coming right away. So when there is something like this in the intersection, but this is of course exactly the condition that the projectivization of K per intersects the Grassmannian, right? That's exactly what Claire is saying, non-trivially. Right? Because the set of the Grassmannian G2V is the set of pure tensors, and I'm saying there is a pure tensor that is in K perp, right? So this is really a very, a kind of familiar-looking condition.
You mean 0? I mean equal empty?
Yes. Okay. Thank you. Right. Yes. So this is okay. So first of all, you see that the resonance will be. For instance, the resonance will be non-zero. So if the resonance is 0, then necessarily the dimension of K has to be at least 2n minus 3. Of course, this is not if and only if, but at some point, if K is too small, then K perp is too big, and it will intersect for dimensional reasons the Grassmannian, so the resonance then will never be 0. Okay, so now let's introduce something like, I'll come to geometry in a second. So I have the projective resonance. And then, so in our papers, this is, now on my blackboard, this looks like the real numbers, but I don't know. It's not what I mean, really. It's bold, so the projective resonance, and this is the proj of S divided by the annihilator. And this is essentially the scheme theoretic resonance. So this is really a scheme. This is a scheme. And I have to say that so there is a lot of papers on resonance, and some are, you know, in topology, rational homotopy theory, some in algebraic geometry, and the scheme theoretic structure of the resonance varieties has been largely ignored, and this leads to various problems. So we kind of go out our way to you know, to define a clear scheme structure. Okay, so this is the projective resonance. So where does this come from, right? So Eduard asked me, is there a good reason to call it? Where does it come from? And it comes from, let's say, one is the Hodge theory and topology. Well, I mean, it's a definition is so general that there will be lots of examples, only in the vector space, in a subspace in which 2B. So you can start with X quasi-projective variety, or even, yeah, Koehler variety. And you can call then V to be H upper H lower one, the singular homology of this. And then V dual will be the cohomology. And then you can consider the cup product map from wedge 2 of H upper one into wedge H2. And the kernel of this is going to be K per. Right? So you look at the kernel of the cup product map, which you can consider for any space, in fact. Let's say you work on a, for Koehler, you want to use the Hodge decomposition and so on. And then you associate a Koszul module to X, so this is V of V and K, and an associated resonance variety, which is the resonance variety of X, and then there's the Koszul module associated to the variety X. So now, do you recognize this, the resonance in this context? So when do you have a space? When do you have two? Okay, first of all, you can pass to holomorphic forms. So when do you have two one forms that wedge to zero? This is Castelnuovo-de Franchi's theorem. Tells you that this happens even only if this. So there is a prototypical example where this happens, and these are Riemann surfaces of genus G, and everything else is pulled back from a Riemann surface, right? So via the Castelnuovo-de Franchi's theorem, which has been generalized by many people to arbitrary dimensions, the idea is the same, like for surfaces. The resonance as a set will be just the union over all fibrations, over all irrational fibrations. So this is a hyperbolic surface, so genus at least 2 of F pullback of H1 of sigma G. Yes? So there is an interesting structure for this variety. It incorporates all the fibrations, all the irrational fibrations over Riemann surfaces. There is an orbifold versions of this and so on, but let me not go that way. And you also see that the resonance in this case is actually a union of linear spaces. Yeah? Okay. So, right. And actually this is very much connected, maybe let me say in words of motivation, to the characteristic variety. Of X. So I take, here there is, you can do many variations and there are many resonances in many more general contexts. I will just focus on the most classical of them. Right? So you look at all the local systems, representations of the fundamental group, and you impose the condition that the associated line bundle has non-vanishing cohomology. And this is what's classically called resonance. Essentially, they are cohomological jump loci. And this is called the characteristic variety. And there is the Kohn theorem. And the Kohn theorem says that if you look at the tangent cone to the characteristic variety at the origin, you are going to get exactly the resonance. And this is, I think, Green-Lazarsfeld, right. So, yes, I should say her name. So, Green-Lazarsfeld, then Boville and Papadima-Suciu and there is a lot of incarnations of this and generalizations. Yeah, that's right. Yeah, let's say green laser sphere. Indeed, they were the first to consider this, say, in algebraic geometry context. Okay, so this is where it comes from. Yeah, well, how about Koszul modules, right? So these are the resonance, but I defined the Koszul modules. So the Koszul modules are, for algebraic geometers, more esoteric objects. They were, at least for me at the beginning, when I looked at them the first time. And how about Koszul modules? So Koszul modules, they have to do with Alexander-Chen invariants. Alexander-Chen invariants. I will be very brief on this. Chen invariants. And I mean, you can have this construction that I described here, essentially to any space I associated a resonance variety and a Koszul module. In fact, I can take any group. So this is a finitely generated group. Yeah, so here you should think of not a finite group, yeah, really some serious group, like mapping class group or Torelli group or something. Take a finitely generated group and you associate you do exactly the same condition, the same construction here. You take V to be H, the homology of the group, and K per to be the kernel of the K-product map at the level of cohomology. And of course, you will get a Koszul module of the group and a resonance variety of the group. The same way, so these are invariants, interesting invariants of any group. So I didn't really prepare, yeah, I should have said that this is more general than, of course, than the previous definition, because I can just take the fundamental group of the variety and I get it. So that is an instance of the last definition. And, okay, so, and then what is this Chen invariant? So let me just say, if you have this group, you can look at this sequence. So you have here the group, you take its commutator, and then you take the commutator of the commutator, and the Alexander invariant of this is this. You declare the Abelianization of the commutator to be BG. This is the Alexander invariant of the group. Alexander invariant of the group. And this can be regarded as a module over the group algebra of G abelian. So this is a module over G over G abelian. This is G abelian. And the action is by conjugation. And then here you take the augmentation idea, so the kernel of the degree map. So this is the augmentation idea. And let me just say what these Chen invariants are. So basically you look at the filtration with respect to the powers of I. So you take this Alexander invariant and you multiply it with IQ, and you divide by IQ plus 1. And now this is going to be a finitely generated abelian group, therefore it's going to have a rank. And the rank of this is what's called theta q plus 2 of G. This is the Chen rank. So I don't want to go into this. They have another, this is really interesting homotopy theoretic invariants. They have there is some history for studying them in various classes, starting from knot theory and so on. That's how they got their name. And right. So and what is the connection to the Koszul module? Well, the connection is the following: that when you look at this rank is always, so this theta q plus 2 of G. I'm sorry for this shift of 2. I hope you take it. I mean, take it as a definition. Is always less than the dimension of W of G. With equality if the group is one formal. In most cases, it's equality. In most cases. So this is the statement. So basically, essentially, if you prove some vanishing here, you have some vanishing on these invariants and so on. And this goes back to ideas of Sullivan and Kane and many other people. Okay, so this is just some sort of, to say these are not out of nowhere, these objects. Any questions? Okay. So, all right, so this is the situation. So these are sort of, as I say, as kind of homotopic theoretic invariants. They can be interpreted in terms of the lower central series of the group and these invariants, but I don't want to go into that. But when you have something about the chain invariants, essentially you will compute, when you know something about the dimension of the components of the Koszul module, you will know something about the chain invariants of the group, and so on. So now I should say that this is the general theory, and as I say, these notions appear in various forms of formalization, and actually, so algebraic appears in our papers. But the more topological, realizations appear also before in this. So the first thing that we looked at, and this is 4 or 5 years ago, was the case of, yeah. Okay, yeah. Take a.
Most cases.
Yeah, most cases, and most cases. I know what in most cases means. One formal. This is, yeah. What?
Is it obvious, this inequality?
It is what?
Is it obvious, this inequality?
Of course. Yes. If I, for instance, especially if I prove that this is 0, then I know that this is 0. And then I have so this is some sort. Then you have some sort of, this is the nilpotence length of this group. So then you bound it. So for instance, you do this for the Torelli group of MG. Yeah, and then you know exactly when this is how we prove that this has a nilpotency length which is linear in G, which is by no means obvious, and we prove it exactly because we compute this invariant and we show it's trivial. Yeah. So this is quite, yeah, and in fact one formal is all the fundamental groups of compact Koehler varieties are one formal. The Torelli group is one formal. There is, of course, yeah, most groups that people in this room have encountered are one formal. Sorry to say it so provocatively. Yeah. So this is really, yeah. So this is definite. So this is the connection. And other questions? Yeah, exactly. And I should say that almost by definition, because if you try to, I could use other words, right? What is one formal means, but it's almost by definition. You sort of, yeah, that you can compute this Alexander invariant infinitesimally. And then there is this whatever algebra, kind of algebraic completion of a certain algebra, and that has a quadratic presentation, etc., etc. You try to unwind this, and then you end up more or less with this.
I guess an obvious consequence of the inequality is also for Q large enough, it starts stationating. Like,
absolutely.
Was this obvious just from the ideal thing, or is it a consequence of this machinery?
It's a consequence of this machinery, and actually of the machinery you get sharp statements or when it starts to stabilize. But this is a very good remark, yeah, actually. Yeah. So the question, the fundamental question here are what? So what can we say? How can one compute these Koszul modules? The dimensions of the Koszul modules. And the first case is the case of vanishing resonance. Right? And the case of vanishing resonance is, of course, when the Koszul module in question, I said that the support of the Koszul module is the resonance. So when the resonance is 0, the Koszul module has finite length. There will be only finitely many pieces that are non-zero. So this is by the more or less what I said is that, to answer Cecile's question, the WQ will vanish at some point. And where does it vanish? That's the question. Right? So the vanishing, so again, vanishing resonance means that what I said, that the K per intersect is disjoint from the Grassmannian. So this is this condition. We work under this condition, and then we have following, well, maybe, I don't know, I write it. So here there is some results, and these are not.
Also, maybe this is very naive, but if you try to look at RVK inside the project V dual, is it just the same as this?
Sorry, if you try to do it with?
Look at the resonance, but put it inside the projective V dual.
Yeah.
Is it the same as the intersection? Because you know, if it's 0, it's trivial or something.
So
like, because you call it resonance variety, so if you put it in P of V dual, what variety do you get? You know, do you get?
Well, so resonance varieties. So first of all, by definition, these resonance varieties are all uniruled.
Ah, okay.
Because there is an obvious, you know, combination. But apart from that, the base can be, I think, any scheme.
Okay.
Yeah. So basically, right. So up to you will never get something of general type, but otherwise, I don't know. Yeah, pretty much you can get anything else.
Okay.
But it has to be uniruled variety. Okay, so this is one result that I mentioned. So this is not so recent. So this was so the case was so there was a theorem that proved with Aprodu. Okay, so okay, myself, Papadima. You can see it's not that recent because Papadima was still alive at the time. So Raicu and Weimann. 18, that we have given, so assume K in wedge 2B.
So it's not any because in the Grassmannian it's something that is cut out by linear equations.
Yeah, sure, right. No, but apart, so there is some. It's pretty much that. Yeah. Anything else can appear up to this construction. Yeah. Yeah. But you can have a lot of embedded points. So actually, I'm going to talk about this. So you have subspace like this, and this is n-dimensional. And then here is this following theorem, which is very simple to state that this is trivial if and only if Wn minus 3 is 0. And of course, this implies, this follows if you, from the definition quite easily, that in fact all the other ones are 0. So if Wk is 0, then Wk plus 1 is 0 as well, right? So this is an optimal statement. It's really an equality of two divisors on the parameter space of such things, and this is an optimal statement, and this was very good in some sense, because it had applications, and one application was another approach to Green's conjecture, and I don't know, like, I don't want to. I say this, okay, so one application of this, but I'm not going to explain what Green's conjecture is. It's about the syzygies of canonical curves, and this was another approach that could be proving Claire's theorem in characteristic, reproving Claire's theorem in characteristic 0, and also providing an approach to characteristic P. So one application was Green's conjecture. And this we did a year later with the same set of people. And we observe the following thing, that you take V to be, I will state it in characteristic 0, but the statement is in any characteristic, except in the characteristic when it obviously doesn't work. So you take the n-1 symmetric product of the two-dimensional complex vector space, and then you look at wedge 2 of V, and this will be S2n-4 of C2, and so on. This is the Clebsch-Gordan decomposition. So this is Clebsch-Gordan. You take the highest piece here, and this is K. And what you have is that you take this V, you have this K in wedge 2 V, and what we prove here is that up to some, in fact, we prove that if C is a generic curve of genus G, the Koszul module associated to this choice, to Sn-1 C2 and to S2n-4 C2, is actually isomorphic to the Koszul cohomology groups, cohomology of C. So this statement, I apologize, I like this probably makes no sense, yeah? But no, not surely it doesn't make sense, but yeah. In any case, this is how it was proven up to this identification. the vanishing probability by Green's conjecture came out exactly of this theorem. So this was an important application of this circle of ideas. But it was, yeah, any question? I don't know whether I should say, yeah.
So you have this implication that Wn minus 3 of Vk because rho implies the vanishing of the higher W.
Yeah, this is general.
Yeah. So more generally, the vanishing of Wp will imply vanishing of the Wp plus 1?
Absolutely. And this is actually immediate from the definition. Yeah, it's a little argument, yeah. So the vanishing Wp 0 implies Wp plus 1 is 0. So the point is to find the minimum p for which Wp is 0. Yeah. And you cannot do better than this, than n minus 3. And you determine also the dimensions of the smallest one, of the first n minus 4. Yeah. And by what I mean by this statement here is that, of course, there is here some SL2 algebra structure on one side, and on the other there is no SL2 algebra structure. But what I mean is that there is a curve which comes from the tangential developable rational normal curve where this makes sense, and the number that you get on that side here are the same as for the generic curve. Okay, other questions?
So does your theorem say also Wn minus 4 never vanishes when the resonance?
It never vanishes.
Okay.
Yeah. And of course, just so generically, for a K generic, Wn minus 3 will vanish. And it will vanish exactly for those cases for which that condition is satisfied. And that describes the Chow form of the Grassmannian cell. So that's a hypersurface in the Grassmannian.
So the two conditions, when it appears in codimension 1, they appear with the same multiplicity?
No. It's a multiplicity, the dimension of V minus 1. It's the same multiplicity that appears in the equality between the Koszul cohomology and the Hurwitz space. But I don't know exactly, due to work of Hirschowitz and Ramanan. But I don't know why. I don't have a good explanation of this coincidence. I don't have. Okay. So this was the situation around 4 years ago. But in fact, so fine. So this is the condition that we have. So okay, we sort of solved the case of one general theorem. Then this is it for vanishing resonance. But then this is a rather significant restriction to have Koszul modules with vanishing resonance. And it was clear that, well, you would like to have such a theorem in general, for non-vanishing resonance, especially if you look at applications, for instance, to fundamental groups or to Hodge theory. Because for the condition, for instance, you look important classes of spaces, like say hyperplane arrangements, where you have really a lot of structure about the cohomology and the fundamental group and so on. You ask, when is the resonance in those cases 0? And the answer is never. So this theorem doesn't apply, simply doesn't apply in those cases. And also for Koehler groups, right? So basically, when is the fundamental group of a variety, when is the resonance of a variety trivial? Well, when the variety is not fibered. But you would like to take into account these fibrations over curves and to say something about the chain invariants in that case as well. So essentially what I would like to say now is that, right, so how about the non-vanishing resonance? The general case. And ideally, one would like to have a formula for computing the dimensions of all the WQs. Yeah, maybe for certain Q high enough. But unfortunately, as was already pointed out here, so you could have all sorts of scheme structures for this resonance, and you cannot hope to have uniform theorems in the absence of any hypothesis to have uniform theorems for these dimensions. So you have to put some conditions, because otherwise you will just have essentially a lot of subschemes of the Grassmannian that appear in the picture. And so I will now I will make a couple of definitions here. So assume that, again, this is very essentially linear algebra. So I look at K in wedge 2B, and then I say that the resonance is, and I define three conditions. So So first of all, I say it's linear. It's a union of linear spaces. So the resonance is a union of subspaces. It's a sub-scheme of V dual. So it's a union from 1 to L of V I hat dual. Okay, where these are linear spaces. So linear spaces in the dual correspond to quotients of the original vector space. Okay, so we have quotients like this. Yeah, so something like this. These are linear spaces. And I already pointed out that for varieties, this resonance is always linear. This is due to from Castellovo de Frankis. Then we say that the resonance is isotropic if it's linear plus the following condition, plus for each condition, so you impose the following condition that wedge 2 of VI dual, hat dual, is actually in K perp. So this is the first condition. This is isotropicity. Okay? So what am I saying here? I'm saying that, okay, so I take two elements here in VI dual. So I have A1 and A2 in the resonance. So these are linear functionals. That means that there exists a B1 and B2 such that A1 wedge B1 is in K perp and A2 wedge B2 is in K perp. Yeah, this is just a definition. And from this, we require that in fact A1 wedge A2, H1 wedge A2 is in K perp. This is the question mark. This is isotropicity, right? So you require something like this, and maybe you will immediately see that in fact it comes from the Hodge relations that for where the Hodge decomposition holds, this isotropicity is almost is there too. So if the mixed Hodge structure of the variety is pure, then the resonance is also isotropic. For smooth projective variety, is something called one isotropic, but almost isotropic, and I don't want to now give the definition of one isotropicity, but essentially you can imagine has to do with this H2. The resonance is controlled by vibrations and has to do with the H2 of the curve in question, right? So this is a very reasonable definitions, if you think a little bit about it, and all the resonances that come from topology, Hodge theory satisfy these conditions. Okay? And now comes the one that is more, that we introduced. And this is joint work with Aprodu, with Raicu and with Suciu. And we say that the resonance now is strongly isotropic. If it's isotropic plus the following condition, plus you have actually quality here. K perp intersection with the ideal generated by VI perp is actually wedge 2 of VI. This is a condition of strong isotropicity. So this is a essentially a linear algebra condition, and I will say in a sentence what is the geometric meaning of it, right? So I should just say that this inequality was isotropicity, and we are requiring we require the other one, the convex inequality. Yeah. So that is the. So what does the second this means? Yeah. So this means, for instance, means that the local. So I can give a local example here. Local example where this fails. So assume that I have V perp is generated is 4-dimensional and it has a basis E1, E2, E3, E4, and I look at K perp to be generated by E1 wedge E2, and then I have E1 wedge E2 and E1 wedge E3 plus E2 wedge E4. So what is the resonance in this case? The resonance means those elements, so that I kept it with one element and I land in K perp. What's the resonance? Right? So the resonance is spanned by E1 and E2 because E1 wedge E2 is in K perp, and that's it. So and this is isotropic. Is spanned by E1 and E2, is isotropic. But it's not strongly isotropic because you see there is this element there which is not in wedge 2, which is not accounted for. Yeah. so you do not have this inclusion. So this is so it's not there. Because this is not a multiple of E1 by G2. Yeah? So this is a typical example where this is not satisfied, and you would like to, anyway, so this is, if you work it out in examples, it has a feeling like a Petri type condition in algebraic geometry. Okay. So what is the point of introducing these conditions? So, I should say, there is tons of examples of Koszul modules in algebraic geometry that have nothing to do with topology. Say you don't like fundamental groups, then you maybe like vector bundles. So there's an example of Koszul modules associated to vector bundles. You take any vector bundle over a variety X, can be of any rank, but let's assume for simplicity that the rank is 2, and I call L the determinant, and I look at the multiplication map, the wedge map. So I can ask the question, if I have this equation, I have two sections and I have this condition. What does this mean? So for one forms it meant that there is a vibration. This also has a transparent meaning. I take two sections of a vector bundle. When is their wedge 0? Well, when they are proportional everywhere. And that means that they span a line subbundle of L, right? So that means that S and T span a line subbundle which I call a pencil. So this is a subpencil of A. And I could define, so I should say now I can define to this situation a Koszul module by taking V to be the dual of the space of sections, and K per to be the kernel of the, this time is not the K-product map but the determinant map, and I have a Koszul module associated to this choice of V and K.
So in this case, it appears naturally with considering the Lazarsfeld Mukai bundle on
Absolutely.
the place of genus. So what does provide your theorem in that case compared to the Green conjecture?
It provides that, so if you want to be in the divisorial case, it provides that you look at an even genus, and then, so I say here, so I look at the even genus is 2A, and you look at the Lazarsfeld-Mukai bundle, which is unique on the K-free surface, that the seam vanishing of the H1 of the seam A of the Lazarsfeld-Mukai bundle. It's a sort of esoteric statement. Of ME. That's what the theorem says. Okay, so in this case, but so this is right. So as Claire observed, so you can define, in fact, for any vector bundle on any variety a Koszul module. Right. So what is then the resonance in this case? So the resonance is of this vector bundle is simply it's a linear vibration. So looks like a linear vibration. So Edward had a nice formulation for this. Look like linear vibration, look like a linear vibration over the variety of subpencils. Over a variety of subpencils. So subpencil means a line subbundle with at least two sections in it. And it's linear because the fibers, of course, have various dimensions depending on how many sections this has. And this has a scheme structure, right? And you can now, I don't want to go into many details, but you can ask now, for instance, if x is a curve. Okay, so I have here a condition which I have some control, all these things here that look sort of linear algebra-like have some geometric interpretation. When is, for instance, rank 2 bundle on a curve strongly isotropic? And there's a local analysis, and I can tell what the answer is. So R of E is strongly isotropic with these definitions, if and only if the bundle in question is very ample. Very stable, not very ample. Very stable. Very stable, so this was introduced by Lomont and by Hitchin, and so this means, this appears in the study of the Hitchin system, and it says basically that there exists no Higgs field, nilpotent Higgs field on for the bundle. This is a pleasant discovery, nilpotent. And the condition is that there is no. So this is some sort of interesting condition, and it just turns out there is a priori what we do here has nothing to do with the Higgs field, but when you put this condition in scheme structure, you want to ask the reducedness of the scheme structure, it's exactly this Hitchin-like condition that appears there. Okay. Yes, fine. So this is now, I should perhaps, right, so get to the results. So fine, so what are the point of these definitions? So the point of these definitions was the following theorem. So everything here is joined with, I already said, but let me also write it with Aprodu, Raicu and Suciu.
If he is only stable, what can we say about RE?
So in general, right, it's a good question. So you can count. So I give you, you take a bundle of degree D, and in general, so if the degree is less than 3G plus 1, then there are no subtensors. If the degree is bigger than 3G plus 1, then you have some sort of linear fibration structure of the variety of such tensors. And if the degree is exactly 3G plus 1, then there are finitely many subtensors. Finitely many, and they will be exactly, the scheme structure is reduced exactly when this is very stable. And you can count in general so this is an analysis that is carried out in one of our papers. Yeah, so it's some sort of twisted Brio-Noether with respect to rank 2 bundles, and so this we didn't necessarily expect to appear in this context, but it does appear. Okay. So, all right, so here's the theorem 1 that we have. And sort of to provide this justification for this, inesthetic set of conditions, yeah? And it says the following, that in fact, basically we are describing the scheme structure of the projective. So we say that the projective resonance is reduced. I don't like how I formulate this theorem, I'm sorry. Okay. Didn't make a good start. So there's two parts of it. Yeah? So the first part is that if the resonance is strongly isotropic, I don't want to. I am not this. Okay, I will formulate a shorter version of it. Yeah. So I'll say that if the resonance is the projective resonance is reduced if and only if the resonance is strongly isotropic. And my hesitation here is that this is not so assume that the resonance is isotropic. Assume the resonance is isotropic. And then you have this equivalence. Because otherwise, if it's not isotropic, there are lots of examples when it's not isotropic, then we have the same condition, we call it separable. The statement says if the resonance is reduced, then it's separable. But here we have an if and only if statement. So this is exactly, if you want, the question is, can you describe locally, can you detect the failure of reducedness of the resonance? And you can say yes, the answer is basically the definition of strong isotropicity. That's exactly the definition.
So in that definition,
bracket means the set of bivectors that are something from the ideal wedge something else.
So, yeah, thank you. No, almost. So this is the ideal. Thank you. I said this. So this is the ideal generated. Ideal generated by this in the exterior algebra. Thank you. This is right. So this is in the exterior algebra. Yeah, the ideal generated in the exterior algebra by this subspace. Yeah. Right. Okay. Now. So now, in principle, now you can have fun that you take a variety and you or a group, or you take a space, and when you have some control over the product map, you can verify whether this condition is satisfied or not. And then, of course, that nobody is just proving theorems that the scheme is reduced. Yeah, this is not so interesting. But why do you want to do this? Because the goal is to get a formula for the chain ranks. And for that, this is precisely the hypothesis that we need. And here is the theorem 2. And it says that the following, that if the resonance, so assume first of all that the resonance, is strong isotropic. And then we write it out as a union of components, as before. So I have these components, V1 up to VL, VL dual, okay? And then we have the following state, the theorem. Then the dimension, so n is the dimension of V. Then the dimension of WQ of Vk is basically the sum from 1 to L of the dimension of WQ of Vi and 0. And this I computed, it was an example just at the first thing I did in this lecture. This is basically Q plus 1. So maybe I continue here writing, this is the sum of so the dimension of this was dimension of V I bar plus Q choose Q plus 2 times the dimension of Vi plus 1. So you have a formula for this. In terms of so assuming this is strong isotopic, assuming you know what the resonance is, and you count how many components are there. There are this many components of dimension 2, this many of dimension 3, and so on. You put it together, and this is the Hilbert series of the Koszul module with strongly isotropic resonance. And I can reformulate this also like this. Is the sum from m greater than 2, and here is q plus 1 times h m times m plus q choose q plus 2, 2 plus q. And where hm is the number of components of dimension m. Okay.
So
And
the VI, they intersect only at 0 or more general?
so, right. So I formulated, no, yeah, there is more general. So this is a z, so, okay. So in the absence of isotropicity, you replace strong isotropicity by separable. And you have three conditions. And then the theorem that we have here, assuming the resonance is separable, forget about isotropicity, you have exactly this. And now you have to say when. I haven't said when. Do we have it for Q sufficiently large, or in fact for Q sharp? And the strongest theorem is that we have this for Q at least the dimension of V minus 3, which is precisely what the bound that was over there. So this is a generalization, obvious generalization of that formula, because there the theorem 1 says that, well, this is 0, and then this is also 0, exactly in this range. If you don't have the isotropicity, we just have this separability, and there are resonance varieties which are not separable. Think of any a smooth projective variety, then we just have this at the moment this theorem only for Q sufficiently large, and then here you don't put 0, but you put the image of K under this projection. But let's focus on this. This is already a good line of example. So this is the formula that we had in mind, and essentially the way we prove it is a Grassmannian geometry. It's not so. It's more complicated, but uses the same ideas that we used in the proof of the first theorem a while ago. And now I should say, well, that's good, but do we have examples? Yeah, when these conditions are satisfied? And yes is the answer. There is lots of examples, and there are and one class of examples, which is very large, is provided by all hyperplane arrangements. No restrictions. So myself, I know very little about hyperplane arrangements. I am in the learning process, but one co-author, actually precisely one, knows quite a bit about them. This is Alex Suciu. And what is remarkable is how little you need to know about hyperplane arrangements to prove this theorem. So, okay, so the point here is now to take, so an application here is to hyperplane arrangements. And this was one of a major source of motivation for studying these invariants. So you start with an arrangement of hyperplanes. So this is an arrangement in, let's say, in C to the D. And what you consider is the complement of the arrangement, of course. Yeah. So you have pictures like this. And this is one of the most well-known ones. So like x, y, z, x minus y, y minus z, z minus x is 0. And you would like, so the homology of this is known, of course. And there is a, I don't know, probably Breeze can't prove this. But there is a presentation that you can find out on Orlik-Salamon, you can find in, for instance, in the book of Dinka on hyperplane arrangements right at the beginning. This is known, and it's combinatorial, it's matroidal. Essentially, the combinatorics of the hyperplane arrangement determines this. And the combinatorics means that you take, well, the intersection poset, yeah? You look at all various intersections ordered by inclusions, and this is the matroidal information, and there is a presentation of the entire algebra in terms of cohomology, and there are as many generators as hyperplanes. Of course, the questions that are open, how about the fundamental group of the hyperplane arrangements, and how about the chain rank invariants, and the lower central series invariants, so this is largely, this is not known, and there is complicated state of affairs. But one thing is that we can, so I should say that this is not determined a priori, by the combinatorics, matroidally. Okay, and here is the theorem here is that and there is a lot of work here in various cases, is that the resonance of any hyperplane arrangement is strongly isotropic. And the only thing that one has to work, and this is really complicated, is the third condition. This condition of separability has to be checked. And as a corollary, you find a solution to a conjecture that was formulated something like 25 years ago by Alex Suciu. And namely, the condition is that, I should say perhaps that the resonance, defining the resonance, this is the components of the resonance, there is a combinatorial procedure. And this has to do with this theory of multinets, which I certainly will not give out, but there are recipes of how, given an arrangement, how to write down all the components of the resonance. For instance, this variety here will have, this arrangement will have 5 components of the resonance, 4 corresponding to the triple points, and there is a 5th one, and so on. So there is this a combinatorial procedure how to do this. And here is Suciu's conjecture then. The Suciu's conjecture says that for any hyperplane arrangement, for any arrangement, you have a formula for the chain invariant. So these are these homotopic theoretic invariants of the group, of the fundamental group of the arrangements, is given by what's written over there. Sum for n greater than 2 of q plus 1 times hm times n plus q choose q plus 2. So this is for any q which is bigger than the dimension of the arrangement minus 3. And so this is basically this is one application that you have. So another side of application that is perhaps more close to the topic of this conference is now Koehler groups, right? So maybe you don't work all the time with hyperplane relations, but algebraic varieties surely you like. And there, hopefully, you take now a smooth projective, a compact Koehler, yeah, and we conjecture there too in our paper that in fact the resonance here, so the resonance in this case is the union over all fibrations, hyperbolic fibrations of f fullback of H1 of sigma c. Yeah, it's linear and it's one isotropic. It's not in general isotropic. So this theorem will not immediately apply. We conjecture that the resonance is again reduced. The projective resonance is reduced. This is we put a conjecture. We don't know of counterexample, and we prove it in various cases. And as a result, as a consequence, you have a formula for the chain ranks of any fundamental group of a Koehler variety. That it is the sum over all fibrations of the theta q of the phi 1 of sigma g. So this is just the fundamental group of a Riemann surface, so these numbers are known. You can immediately write them down. And you see that this is kind of an interesting formula because here you have a sum over all fibrations of some known quantities, and here you have something called the fundamental group of the variety. And there are conjectures here, there are, for instance, conjectures on the number of possible fibrations of a variety. Catanese, for instance, conjecture that there is no surface which is Kodaira fibered in more than 2 ways. This is a notorious conjecture. If you talk to him, for instance, and nobody produced an example, but this is something that, gives you a bounding principle. I'm not sure it's going to give you exactly 3, but you have something that is bounded by the surface. And here you have a sum of quantities, positive quantities over all fibrations. Anyway, so that's...
That was when X is a surface?
That was when X is a surface, and there are variations for higher dimensional.
Could you please repeat your condition?
Right. So there are Kodaira fibration. Kodaira fibration is a submersion. X over B. Yeah. Exactly. So you have X over B and sigma G. Okay. All the fibers are smooth. It's submersion.
Genus at least.
Yeah, genus is at least. Yeah, right. Hyperbolic. And then there are also examples with 2 fibrations. Actually, all Kodaira fibrations are sort of with 2 fibrations. And then you take, essentially it's a cover, it's a double cover, you take 2 curves and you take some double cover of the product and you do various things. Yeah?
Why not just the product?
Yeah. So then the conjecture is that you cannot do better. So for any X surface, there are at most 2 Kodaira fibration structures.
Why do you want Kodaira fibrations?
Because otherwise you can do better.
Where is smoothness used in this?
No, so that's a fair point. So for this formula, there is the Kodaira fibration structure doesn't appear. But I think there is various versions of this formula. What I say, you would like to bound the number of fibrations, in terms of the homotopy of the variety in question. Right, and this, so this I move with the side remark. I'm not sure, what I know is that we have examples here when this formula, when the resonance is reduced, each time is reduced, the same proof will produce a formula like this. And then that is a formula where you have something bounded. It's a sum of positive quantities over all vibrations, so then you are pretty constrained, how many vibrations you can have.
You need to assume that the curve is of general type, otherwise you could just take.
No, G is at least 2, yeah.
Okay.
So always here, in the beginning I said that when you look at the resonance of a Koehler group, right, so this is G greater than 2. Otherwise, right, yeah. This is Castellovo, Frankis is, yeah. It's over. Okay, so thank you very much. I'm sorry for going.